Hey there, and welcome in. Today, we're going to really get our heads around AWS route tables, and by the end of this video, you'll understand exactly how AWS decides where every piece of your network traffic goes. Think of a route table as the map your network reads before it sends anything anywhere. It's one of those topics that feels mysterious at first, but once it clicks, a huge amount of AWS networking suddenly makes sense. So let's take it slow. Build it from the ground up, and turn this into something you genuinely understand rather than memorize. So what actually is a route table? At its heart, it's just a set of rules, and each rule is called a route. Every route answers one simple question. If traffic is headed to this destination, where do I send it? Imagine you're at a big airport, and there's a signboard that says, flights to the east, go to gate A, flights to the west, go to gate B. The route table is that signboard for your network packets. Each packet carries a destination address, and the table looks at that address and points it toward the right exit. No table, no directions, and your traffic has nowhere to go. Let's picture this inside a VPC, which is your own private network in AWS. Here we've got a VPC split into two subnets, a public subnet with an EC2 server that's allowed to face the internet, and a private subnet with an EC2 server that should stay hidden. In the middle sits the route table, and it's the thing choosing the path. It can send traffic locally, meaning it stays inside the VPC. It can send it to an internet gateway, which is the door out to the open internet. Or it can send it to a NAT Gateway, which lets private servers reach out without being exposed. The route table is the decision maker that picks one of those roads for every packet. Now let's walk through what actually happens, step by step, when traffic moves. First, a resource, say your EC2 instance, sends traffic towards some destination address. Second, AWS looks at which subnet that resource lives in and pulls up the route table attached to that subnet. Third, it scans the routes in that table and finds the best matching one. This lookup happens automatically, instantly, for every single packet. You don't trigger it or manage it by hand. It's the invisible traffic cop standing at the edge of your subnet, checking the signboard before letting anything through. And that lookup has exactly two possible outcomes. Either a route matches the destination, in which case the traffic is happily forwarded to that route's target, the gateway or resource it points to, or no route matches at all, and in that case the packet is simply dropped. It just disappears, with no error sent back to wherever it came from. This is one of the most common sources of confusion for beginners. They set up a server, it can't reach the internet, and they assume something's broken. Often nothing is broken. There's just no matching route, so the traffic quietly vanishes into nothing. The table only knows the paths you've given it. Here's the one route you'll always find in every single route table, the local route. You can see its destination is the VPC's address range, in this case 10.0.0.0/16, and its target is simply labeled local. This is what lets every resource inside your VPC talk to every other resource inside it. Your web server can reach your database, your app can reach your cache, all because of this local route. And here's the key thing. You cannot remove it and you cannot change it. AWS bakes it in automatically and protects it, because internal communication is the whole point of having a network. It's the foundation everything else is built on top of. Okay, this is one of the two parts people find confusing, so let's slow right down and spell it out plainly. When you create a VPC, AWS automatically creates one route table for it, called the main route table. The important thing about the main table is this. It's the default fallback. Any subnet that you do not explicitly attach to another table will automatically use the main route table. You don't choose it. It just happens. A custom route table, on the other hand, is one you create yourself by hand and then deliberately associate with the specific subnets you choose. Now, why would you ever bother making a custom one? Because different subnets often need completely different routing rules. Picture this concrete before and after. Before, you have a public subnet that should reach the internet and a private subnet that should stay sealed off. But if both are just sitting on the main route table, they both get the exact same rules, so you can't give one a path to the internet without giving it to the other too. After, you create a custom public route table with a route sending 00.0.0.0 to the Internet Gateway and associate it only with the public subnet, and a separate custom private route table sending 0.0.0.00 to a NAT Gateway for the private subnet. Now each subnet behaves exactly as it should. And here's the classic mistake to watch for. People build a brand new private subnet, forget to associate it with a table, and it silently falls back to the main route table. If that main table happens to have a route to the internet, your supposedly private servers are now quietly exposed. So the rule of thumb many engineers follow is to keep the main route table locked down with no internet route, and put every deliberate path into custom tables you control. Let's look closely at a public subnet's route table. You'll see two routes here. The first is our familiar local route, 10.0.0.0/16 pointing to local, keeping internal traffic inside the VPC. The second is the one that makes this subnet public, destination 0.0.0.0/0, which means absolutely any address anywhere, pointing to the Internet Gateway. That 0.0.0.0.0 is the catch-all. If a packet doesn't match anything more specific, it goes out this door to the open internet. But here's a subtle trap. This route alone is not enough. Your instance also needs a public IP address to actually be reachable from outside, and your security group and network rules have to allow the traffic too. The route opens the road, but the IP and the security rules decide whether the car is allowed to drive on it. Now compare that to a private subnet's route table, and notice the one crucial difference. The local route is still there, same as always, but the catch-all .0.0/0 route points to a NAT gateway instead of an Internet gateway. This is a beautifully clever bit of design. A NAT gateway lets your private servers reach out to the internet to download updates, call an external API, pull a software package, but it does not let the internet reach back in to start a connection. It's a one-way valve. Think of it like the staff-only back door of a restaurant. The staff can step out to take deliveries, but customers can't wander in through it. That's exactly how you let private servers stay useful while keeping them safe from the outside world. Now we get to the second idea people stumble on. What happens when more than one route matches the same packet? AWS uses a rule called longest-prefix-match, and the short version is, the most specific route always wins. On screen you can see a 16 route, which is less specific, and a 24 route, which is more specific, and the 24 wins. But don't just memorize that. Let's actually understand why on the next slide, because the reasoning is the part that makes it stick. Here's the why, step by step. A packet is heading to the address 10.1.1.25, and three routes in the table could match it, a /24, a 16, and a .00/0. Now, that slash number is the secret. The slash number tells you how many bits at the front of the address have to match exactly. So a 16 means the first 16 bits must match. That's a wide net, covering everything from 10.1.1.0 all the way through 10.1.255.255. A 24 means the first 24 bits must match. A much narrower, tighter range, only 10.1.0 through 10.1.255. The bigger the slash number, the more precise and the smaller the range. Now watch our address, 10.1.25. It falls inside the /24 range. It also falls inside the broader /16 range. And of course it matches .0.0.0.0, which matches everything. So all three are valid. Why does AWS deliberately choose this 24? Because the most specific route is the most precise, most intentional instruction you gave for that exact address. When you wrote a rule that narrow, you were clearly saying something deliberate about that small block of addresses, and a vague catch-all shouldn't override your precise intent. So the packet to 10.1.1.25 gets sent to the VPC peering target on the /24 route. And one more thing that trips people up. The order of routes in the table makes absolutely no difference. AWS doesn't read top to bottom and stop at the first match. It looks at all of them and picks the most specific. It's about precision, not position. Quick one, if this is the part that finally made longest prefix match click for you, hit subscribe and give it a like so you don't miss the rest of the series. All right, back to it. Let's gather up the different places a route can actually point, because the target is just as important as the destination. Local keeps traffic inside the VPC. That's our unremovable friend. The IGW, or Internet Gateway, gives full public internet access in and out. The NAT, or NAT Gateway, gives private outbound-only access. Reach out, but nobody reaches in. And then there's a whole family of others. VGW for a VPN gateway connecting to your on-premises office network, PCX for VPC peering linking two VPCs together privately, and TGW, the transit gateway, which acts like a central hub connecting many networks at once. Each target is just a different kind of door, and your route picks which one the traffic walks through. It's worth pausing on what happens when routes change, because this is where real outages come from. If you delete a target, say you tear down a NAT gateway, every route that pointed to it instantly breaks, and the traffic that relied on it starts getting dropped. If you replace a route, new traffic immediately starts following the new path, sometimes in ways you didn't fully expect. This is why you change routes carefully in production. A single edit to a route table can quietly take a service offline, because you're not touching one server. You're rerouting traffic for every resource in that subnet at once. Treat route changes with the same respect you'd give to flipping a switch in a live power grid. Let's pull the big lessons together. First and most important, route tables control your entire network flow. They are the brain deciding where everything goes, and almost every connectivity question in AWS eventually comes back to them. A public subnet gets its reach by routing point 0.0.0/0 to an internet gateway. A private subnet gets safe outbound access by routing 0.0.0/0 to a NAT gateway instead. Get those two patterns firmly in your head, because they are the backbone of nearly every real-world AWS network design you'll ever build. And here's the rest of the essentials to carry with you. Every route table always has that local route, automatically present and impossible to remove, keeping your VPC talking to itself. When several routes match, the most specific one, the one with the biggest slash number, always wins, because it's your most precise instruction. And always change routes carefully, because one edit reroutes traffic for an entire subnet. Honestly, once you truly master your routes, a whole lot of AWS networking stops feeling like magic and just clicks neatly into place. And that's a wrap. Thank you so much for watching and for sticking with me all the way through. If this helped route tables finally make sense, please like, share, and subscribe for more cloud and AWS videos. It genuinely helps the channel grow. And just so we're clear, this video is for educational purposes only. AWS, Amazon Web Services, and all related names and logos belong to Amazon, and I'm simply using them here to teach. I'm not affiliated with or endorsed by Amazon Web Services. Take care, keep building, and I'll see you in the next one.